Yeah, so before we start, do you have any questions about what we talked about in the first lecture?
Sir, in the
Yeah.
last lecture, in one of the slides you say 78% of all the nodes were present in a big diagram. So we are considering that as it was the whole network. So is there any percentage that if I include all the nodes at least with this percentage in this network, then that I can consider that network as a complete network?
Okay, so the reason why 70% was mentioned was as follows. So suppose you have a network, okay? Now it could be that actually the network consists of disconnected fragments, okay? So the particular network that I was showing, the protein-protein interaction network of East, what happens is that there would be quite a few proteins which interact with each other but not with other proteins. Okay, so in such a situation, if you are interested primarily in looking at things like how does information from this particular point of the network move to that particular point of the network, it's not very useful to consider these two disconnected fragments, because obviously, because there are no paths connecting this fragment with that fragment, uh, all the measures that you are going to calculate would give you unreasonable values like infinity and so on, right? So then you focus on the largest connected component, okay? So I gave a kind of a schematic picture yesterday when I'll just rub this out. So suppose you have so you can call this a network, right? So you can count how many nodes there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you'll say n equals 12, and you can even count the number of edges. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you'll say there are 10 edges. Okay, but as the numbers themselves will tell you that obviously there would be a few nodes which would be disconnected. Okay, so actually if I just tell you there are 12 nodes and let's say there are 10 edges, would you be able to immediately say that there would be disconnected components? What's the minimum number of edges required to make n nodes connected? What do you think? So you have n nodes, and I want to know what is the minimum value of L exactly, such that the n nodes are connected. Okay? And the answer is L minimum would be n minus 1, because you can create a chain where each node is connected to another node, that in turn is connected to another node, that in turn is connected to another node, and so on. Okay, so if you count, there would be n minus 1 edges connecting this n nodes. Okay, and this is the smallest number of edges that you can get away with. Okay. If you have any fewer edges, necessarily there would have to be some nodes which are not connected. Okay. Now, even if you have L greater than this, okay, so suppose you are told that L is greater than n minus 1, even in such a situation, you could of course have nodes which are disconnected, because all that this tells you is that in principle you have enough number of edges to connect all the nodes, but it does not tell you whether in reality, the network that you're considering would have all the nodes connected or not. Okay, so for example, you could have a situation where for example, you could have a situation like this. Okay, so if you count, there are 5 nodes, okay, and 1 2 3 4 5 6 edges. Okay, so n equal to 5, l equal to 6 does satisfy that criteria. However, you can see that what is happening is that 4 of them have created a fully connected cluster. So this is also sometimes known as a clique. Okay, a group of nodes who are each connected to everyone in that group is called a clique. Okay, so what has happened over here is that you have had a clique formation and one node has been left out. Okay, now under what condition would you be guaranteed that every node is connected to the network? No, as I just mentioned, that is itself not sufficient, right? Yeah, so of course, trivially, if every node is connected to every other node, then you'd be guaranteed that every node is connected. Okay, and what is that number? So it's a problem in combinatorics, right? So you have n nodes and every node has to be connected with n minus 1 other nodes. Okay, so the total number of edges would be n times n minus 1 because every node would have to connect to n minus 1 other nodes. However, if you're considering undirected networks, then a connection from A to B would also imply a connection from B to A. So in a sense, you're double counting, right? So you have to take a factor of half. Okay, so that's why you have a number NC2. So this is the total number of all possible edges between n nodes. Okay. So if you have NC2, if you have L equal to NC2, of course it's guaranteed that every node would be connected with every other node. But of course in reality, even if L is somewhat smaller than NC2, you'll be guaranteed that every node is connected. But oftentimes, unless you have some other additional information about the network, it's often very hard to figure out whether you do have disconnected fragments or not. So for example, suppose I asked you that, let's say I give you this information about L and N and ask you, well, what would be, let's say, the typical distance between two nodes in the network. Okay, I will in fact talk about paths in a moment. That's essentially the content of today's lecture, part of today's lecture. But let's take a look at it, using these toy models. So, suppose you are told that you have n nodes and you have L equal to n minus 1 edges. You would construct this, let's say, and what is the average degree of this graph? Can you estimate? Okay, so what was degree? Degree was the number of connections that each node has. Okay, and so therefore average degree would be the mean number of connections per node. So approximately what would be the average degree of that graph?
Because the last and first node,
Yeah,
they are degree 1.
true, but let's assume that n is quite large. Okay, in which case the end effects can be ignored. Okay, so you would say that the average degree is 2, right? There is another way to get this result. So one way to think about this is as follows, that what is average degree other than the total number of links divided by the total number of nodes, okay, multiplied by 2, because otherwise again you'll come into the problem of double counting. So what do I mean? So if you are asking that, suppose I'm given the degree, okay, so let's denote the average degree by this symbol, angular bracket k, because k is typically the symbol we use to represent degree. Okay, so suppose you're given the mean degree. So one way we can think about the mean degree is that the mean degree multiplied by the total number of nodes, okay, gives me an estimate of the total number of edges in the graph. But remember, you have to now divide this by a factor of 2, simply because you're counting the average. When you're counting the average degree, suppose I have 2 connections and you have 2 connections, but let's say I'm connected to you, so then actually one of the edges that I have is common with the one of the edges that you have. Okay, so consider that every one of the degrees, every one of the connections which contribute to a degree of a particular node is also contributing the degree of other nodes. Okay, because every edge is counted twice when you're looking at what's the number of connections that a node has. So that's why you have to consider this factor of half, and so this gives you a relation between L, N and average degree. Okay, so now given the L and the N, I can work out what is the average degree simply by using this relation. So again, this would tell me that the average degree is around 2. Okay, now, yeah, for directed networks this is no longer true, because for directed networks you have to now consider the fact that if a connection exists from A to B, it need not exist from B to A. Okay, so each link has to be considered uniquely. Okay, so the factor of half no longer appears when you're considering a directed graph. Okay, also for directed graph you have to distinguish between invert connections and outward connections, but more about that in a moment. Okay, okay, so suppose you are told that you have n nodes and n minus 1 edges. So you would think, okay, maybe the system looks something like this. And then I ask you, okay, what's the typical distance that you have to travel to go from any node to any other node? So in other words, what's the average path length? So I'll talk about that in detail, but you can easily see that typically it would require order of n hops to go from one point to another point. Okay, if you just work out the average. Now you would think, okay, so that means that if I have n nodes and n minus 1 edges, typically the average path length would scale as n. But now I tell you that what if I give you a network which looks like this? Okay, so how many edges are there if there are n nodes? Sorry? No, I mean, if I'm calling the number of nodes to be n, so in that case what is L in the star configuration? Again it will be n minus 1, right? What's the average degree? Again it will be 2, okay, because it just follows from L and N. Okay, however, if you look at the typical path length, what will the typical path length in such a system? To go from any node to any other node, typically how many hops do you require? 2, right? So this is a constant. It's not even a function of n anymore. Okay, forget about being a linear function of n. Okay, so you can see that just knowing L and N, and by extension the average degree, does not tell me anything about what would be the typical path length of a network unless I'm given some more information. So in this particular case, the highest degree of the network. Okay, so if you tell me that apart from the average degree being 2, the highest degree of the network is order of n minus 1 in fact, okay, then I would immediately know, okay, so it looks like a star, so in all probability the path length would be extremely short. Whereas if you tell me that the maximum degree is like close to the average degree, so it's something like 2, so then I would know it's more like a chain, and therefore the path length would kind of scale as n. Okay, okay, so the specific question you asked about, why we look at this largest connected component is because now if I want to ask questions like what's the average path length of the network, so I have a network which looks like this. So suppose I am asking what's the average path length of such a system. Okay, so as long as I confine my attention just to this fragment or just to this fragment, I'm okay. But when I'm starting to talk about average path length and considering paths going from this fragment to this fragment, I get in trouble because the path length from here to here is infinite. Okay, and so basically I'll end up with a nonsensical average measure. But suppose this essentially corresponds to the bulk of the network, so then I can just focus my attention to this, obtain all the properties and be done with it. Okay, so that's why typically when we are dealing with networks which have several fragments, people usually look at the largest connected component. Okay, and of course you are kind of in safe territory if it turns out the largest connected component happens to be the bulk of the network, and in the example that I was talking about, it happened to occupy almost 80% of the network, so you would be forgiven for essentially ignoring the rest of the network. Okay, all right. Okay, so let's I think I need to probably change, excuse me, I think I need to change the resolution of this because this is not coming. Yeah. Yeah, okay, good. All right, so in today's lecture, I will essentially talk about some of the important metrics that we use to identify aspects of the network structure. So I mentioned that just knowing the number of nodes and edges doesn't really tell me too much about how the network is structured. So I might need to know a few more things like what's the average path length, what's the maximum degree, what's the degree distribution, and so on. So I'm going to define all these quantities in today's lecture, and I'm going to try to connect it to some real systems and to show how you can use this metrics. Okay, and of course, although networks appears to be rather new subject, its roots goes back extremely long time. In fact, we trace it all the way to Leonhard Euler, who lived in the 18th century, and network science essentially is said to be born by Euler's attempt to solve this particular problem called the bridges of Königsberg. Okay. So Königsberg, which is now known as Kaliningrad, was a city in Prussia, and at that point of time there used to be these 7 bridges across the river flowing through the city, and very common kind of a mathematical entertainment puzzle that used to make its round was the question, is it possible to find a walk that will cross the bridges once and only once but go through all of them? Okay. So you can of course try to do it manually. So you could, like, solving a maze, you can start at any point and you say, okay, let's see if I just trace my path through here like this. Is it possible to find a path which would go through all of the bridges once and once only? Okay. You try this one. So for example, you start here, you go through like this, like this, like this, but then you are stuck here because there's no way you can get to this bridge without actually going through this bridge, which you've already walked, right? So then you say, maybe I started wrong, so let's start here. So you go like this, this, and let's say this, 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 but then again you're stuck because you can't again find this. So you can do this manually, but Euler decided to cut through this, mess of, trying to find manually solutions, and came up with a very elegant argument, which I'll come to in the middle of my lecture when I talk about Eulerian paths, which showed the power of graph theory in solving problems which seemed like, requiring a lot of trial and error kind of approaches. And this, to some extent, a humble beginning, led to the explosive growth of graph theory, and it was more or less confined to mathematics till about the late 1990s, when in the late 90s, suddenly a lot of things happened which made networks a very popular topic, not just to mathematicians but also to physicists, computer scientists, social scientists and all. Okay? And one of the reasons why networks became so popular was that it became a way to solve the enormously practical problem of how to search the World Wide Web. Okay? So it's told that when the World Wide Web was developed by Berners-Lee and others, they were doubtful about its usefulness because one problem that they could not figure out how to solve was, how do you find a piece of information among the huge number of pages that essentially constitutes the web? Okay. So suppose you want to find a very specific piece of information which is located in one particular page, but the total number of pages that constitute this web is just increasing exponentially. So in such a situation, it's simply not possible to keep some kind of a manually curated list of keywords through which you basically go through in order to find something that you're interested in. So it's like the proverbial searching for the needle in the haystack. And what happened in the late 90s was that a young company called Google came up with a rather innovative idea of how to do this search. It's often called the PageRank algorithm. But the essential idea was that they said that let's not consider all pages to be equally important, but rather weight them in terms of their importance. And how do you define importance? You define importance in a rather circular manner. You say that important pages are those to which other important pages link to. Okay? So this particular algorithm was in fact motivated by graph theory or network science using this concept of node centrality. Okay? So the concept of centrality, of course, has many definitions. There are many different types of centrality depending upon how you define it. But the idea is that it's a property which is associated with a particular node. It measures how important it is respect to the other nodes in the network. Okay? And the particular node centrality measure that the Google PageRank algorithm was based upon was the concept of eigenvector centrality. Okay? Now you might ask that, well, I mean, how do you get around this circular definition? Because essentially you are saying that the importance of a page is determined by how many other important pages link to it. But the whole concept of importance then becomes defined in a circular manner. Okay? And the way you do it is to convert it into a linear algebra problem and use the idea of eigenvectors. And so let's see how the algorithm's basis in graph theory works. So consider it as follows, that each node when you start with is given an importance score which is proportional to the sum of the importance score of its neighboring nodes. Okay, so this is directly translating this phrase that I mentioned before, that your importance is based upon how many other important nodes you are connected to. It's not how many you know, it's who you know. Okay. So you would of course say that, but then how do I start at all? Because if my importance is based on the other node's importance, then I basically try to go to the other node and see how do I calculate its importance, and then it just essentially the problem just keeps recurring every time I try to go to a particular node and measure its importance. Well, let's just say that we give some random initial score to each node. Okay, let's call it xi at time 0. Okay, so the ith node is given an initial score of xi at time 0. And for simplicity, you can just choose it to be the same for all the nodes. So, you just set it to 1. Okay. And now you say that, okay, this was my initial guess. Now I will give a better measure of this by essentially replacing the importance of the ith node at the next iteration by summing over the scores of all the other nodes which are connected to it. Okay. So how do you do that? Well, one way to do that is simply to take the product of the aij element of the adjacency matrix with xj. So if j is connected to I, aij would have 1, aij would be 1, and so therefore it would contribute to the sum. On the other hand, if j is not connected to I, aij would be 0, and so therefore it would not contribute. Okay? So the simplest is to just have a right hand side which looks like this, just a product of the corresponding element of the adjacency matrix with the score of the jth node. So it's best at this point to go over to a matrix notation. So you just say that if I represent the importance of all the nodes as a column vector, then I can write it as the x vector, and for each iteration I would have a particular vector, and what I'm doing by this process is basically updating this column vector. So the x vector at time 0 multiplied by the adjacency matrix gives me the x vector at iteration 1. Okay. So now you can iterate this again and again, and after t such steps you notice that what you would get is essentially xt, which is a operated on x naught t times. So basically you get a to the power t operated on x naught. So that would be the value of xt. Okay, so what we have done is that we have now converted into a algebraic equation. So I would now go over to the eigenvalues and eigenvectors of this matrix. So I say that, okay, I can express this vector in terms of a linear combination of the eigenvectors of A. So if I say that the eigenvectors of A are Vi, I can just represent it as some linear combination where this constants Ci refer to basically the factors which essentially represent the linear combination. So now I can rewrite xt as a to the power t times x naught is now represented as just this linear combination of the eigenvectors. Okay. Now up to this point I'm just using this representation. But at this point you realize that what is this? This is nothing but an operator operating on its eigenvector. Okay. And as we know from linear algebra 101, a matrix multiplied with its eigenvector gives what? The eigenvalue times the eigenvector, right? I mean, that's in some sense the definition of eigenvalue and eigenvector. So essentially, if V is the eigenvector of A and lambda is the eigenvalue of A, then I would have essentially this relation. Okay, and that's precisely what I'm going to use here. So I'm going to replace a raised to t vi with the corresponding right hand side of that eigenvalue equation. So it just becomes lambda I raised to t vi. Okay. So now what I can do is, so there are all these different eigenmodes. So what I'm going to do is I'm going to take the largest eigenvalue outside the summation sign and represent all the factors in the summation as a ratio of the ith eigenvalue to the first eigenvalue, where the first eigenvalue is the largest eigenvalue. Okay. So I can rewrite it as now, so I take lambda 1, which is the largest eigenvalue outside, so I get lambda 1 raised to t summation over I, the linear expression factors times the ratio of all the other eigenvalues to the largest eigenvalue raised to t vi. Now, by definition, this quantity is less than 1, less equal to 1, right? So if a quantity is less than 1, if I raise it to a sufficiently high power, it would essentially go to 0. And so, as t tends to infinity, I'm guaranteed that the only term which survives is actually just the leading term, corresponding to the largest eigenvalue. So now, essentially, I can say that what is my importance vector? It's nothing but proportional to the eigenvector of the corresponding to the largest eigenvalue of the adjacency matrix. So now I can say that the centrality measures of each node essentially can be obtained from the components of the eigenvector corresponding to the largest eigenvalue, because essentially it satisfies this eigenvalue relation, this eigenvalue equation. Is that argument clear? If not, please ask. Yeah.
First, you are finding the degree of that node. When you were suggesting that we take each exile at 1, taking the value of 1 for each exile. So, initially we are calculating the degree of when you are writing that it's I, the summation of A, I, J, so you are finding the degree of that.
In a sense, yes. So what I'm doing, but it is not exactly just proportional to degree, okay? Because now what will happen is, you're right, in the first round, it will just be the degree. But in the next round, suppose I'm connected to, let's say, 10 nodes, but each of those 10 nodes have no other connections, okay, or very few connections. So that would contribute a very small factor to me. In fact, if they all have no other connections, then essentially it would be the end of that iteration, right? However, if the 10 nodes that I'm connected to each have 10 other connections, then that would now contribute a very large factor to me. So essentially, beyond the first step, I'm now looking at what are the connections of my neighbors. Okay, so if I'm connected to lots of high degree nodes, I tend to increase my importance, as opposed to if I'm connected to extremely low degree nodes. Okay, so it's not just my own degree, it's also the degree of my neighbor's degree which contribute to this. Okay, which is in fact intuitively what the PageRank algorithms work effectively does. So for example, it would score extremely highly pages which everyone visits. Like for example, let's say IRCTC would have an extremely high score, okay, because other pages would link to it. Okay, but let's say my personal homepage would not have extremely high score, simply because it would probably only connect it to the institutional website and so on. Okay.
Does it mean that if I ask my friends that this would put the link of my website in their website, then it will increase the rank of my website?
That is in fact precisely what that's the reason why the Google never releases the exact algorithm that its PageRank algorithm uses, because there are certain weightages it uses for various things. But if they just use this thing blindly, of course, and you would know this, of course you would be able to fool the algorithm by doing this operation that you would just say give lots of links to my page and so on. Okay, and Google of course knows this, so essentially it tries to break through this by using other tricks of trade, which are all trade secrets.
So is this something like advertisement in various websites?
I'm sorry.
They put the ads in the website.
Yeah,
Is this something like that using to increase their centrality?
ads in their website doesn't.
Suppose just example you say the IRCTC. So if I put one of my pages ad in the IRCTC website, so obviously it will increase my centrality because I am connecting with very important point.
Okay, that way. Yeah, so if you can convince, very high degree nodes to have a link to your page, of course, that would raise the importance of your page. But of course, convincing IRCTC to put a link of your page would cost a lot of money, right? Okay, so let's then take a step back and look at some definitions of these different metrics that we associate with network, because we'll be using this metrics again and again. Okay, so this is something that we mentioned briefly in yesterday's lecture, that networks could be of different types depending upon the properties of their links. The simplest kind of networks are where the links are undirected. So if a connection exists between A to B, you assume that connection also exists from B to A. Okay, and this of course means that the corresponding adjacency matrix is symmetric. If Aij equal to 1, Aji also equals 1, and if Aij equal to 0, it implies that Aji equal to 0. Okay, so undirected network and a symmetric adjacency matrix are essentially interchangeable. On the other hand, if you have a directed network where you say that just because a path exists from A to B does not tell me whether a connection exists from B to A, in such situations we have a directed network and correspondingly generally an asymmetric adjacency matrix. Now, I also mentioned that adjacency only tells you about whether a connection exists or does not exist. But I might be looking for properties which go beyond such information. So for example, I can have many friends, but there are some friends with whom I talk more often than others. So how do I represent this quantitative heterogeneity in my links? So one way to represent this information is to actually provide not just the adjacency information but also the weight information. Okay, so what's the strength of interaction? Not just whether interaction exists or not, but the strength of interaction between two nodes. So that would correspond to a weight matrix. Okay. On the other hand, there could be interactions which differ in the nature, in the very qualitative nature. So for example, with some people I could have extremely friendly relations. With other people, I have an equally intense relation, but they're of an antagonistic kind. They're enemies. Okay. Now you might say, okay, why consider enemies in your social network? Well, for certain applications, it might be equally important to consider antagonistic relations, because they often tell me why certain nodes will not cluster in certain groups but cluster in different groups. So if I completely ignore antagonistic relations, I will not be able to say anything about why that particular kind of clustering happens. So for applications where I need to know the nature of the interactions, whether it's positive kind of interaction or negative kind of interaction, those kinds of networks are represented by signed graphs, where for each link you associate a plus or a minus representing a affiliative or an antagonistic interaction. Now in biology, this is often very important, because you could, for example, have a neural network where a neuron could either have a excitatory interaction or an inhibitory interaction with another neuron. It's excitatory when a neuron fires, it would make it more likely that the neurons that it connects to will also fire, whereas it's inhibitory when it fires, it makes it less likely that the neurons with which it is connected will fire. Okay. And you have similar kinds of activatory inhibitory interactions also, for example, in genetic regulation, where when a particular transcription factor can act as a promoter for the expression of another protein, or it could inhibit the expression of another protein. So you could have positive relations as well as negative relations. So in order to represent those kinds of qualitatively different interactions, you have to consider signed graphs. Now, I mentioned path length. The reason why often we are extremely interested in questions of path length is because this tells us how quickly the influence or the disturbance in one part of a network can propagate to a different part of the network. Or it could be you are interested in to know whether the excitation in one neuron, how quickly can it result in the excitation of another neuron located in a different part of the network. Or if you're interested in things like information, so you could say that, okay, suppose I have an information packet that originates here, how quickly can it find its way to a node at a different part of the network? So typically these kinds of questions can be addressed by calculating the path length in the network. So the path is defined as follows, that when you want to know what's the path length between A to D, you typically have to first find out the path in terms of the sequence of nodes that you have to go through in order to get from A to D through edges. Okay, so as you can see, between A and D, there are no links. So in order to go from A to D, you have to essentially go through intermediate nodes, which are such that every pair has an edge associated with it. So you can go from A to B, you can go from B to C, you can go from C to D, and in this way you can find yourself from A to D. And the path length is essentially the number of such edges that you have to go through to go from A to D. So in this particular case, of course, it's non-unique. So you can go from A to D either by following this path or following this alternative path, which is A, B, E, D. In both cases, the path length is 1, 2, 3 for A, B, C, D and 1, 2, 3 for A, B, E, D. Okay. For directed networks, we can also define a directed path and a directed path length. So for example, to go from A to D, you can follow the path A to B, B to E, E to D. But notice that if you take a slightly different path, so that for example, if you go from here to here, you are stumped because all the arrows are actually pointing inwards. So there's no way you can proceed further, so you will not be able to go from A to D using this path. So that's the difference between directed and undirected network, that in undirected network, typically many more paths are possible than in directed network. So often you find that in directed networks, a path may exist from one node to another node, but the reverse path may not be possible. The other thing is that normally we do not consider paths which essentially are going through the same edge over and over again. So for example, you could have said that, why don't we consider a path like this? A to B, B to C, C to E, E to B, B to C, C to D. Okay, you could if you want, but typically we consider self-avoiding paths where each edge is traversed only once. Okay, and that's because typically we are interested in the paths of shortest length. Okay, now how do we find the number of paths of a given length? Okay, again, we take the help of the agency matrix. Now, what is the agency matrix actually telling you? It tells you that if Aij equals 1, that means there is a path of length 1 from I to j. Okay. Now you'd say that, okay, that's very useful, but suppose a path doesn't exist from I to j. I'd like to know whether a path of a higher length exists from I to j. So Aij equal to 0, but I want to know, is there a path of length 2? So is there an intermediate node, some k, which I can go through and then eventually get to j? So how does the agency matrix help me in such a situation? Well, very simply, you notice that if the product aik times akj is 1, that means there is a path of length 2 from j to I via k. Okay. So that immediately tells you that, wait a minute, if I take powers of a, okay, so if I raise a to the power 2 and look at now all the matrix elements which are non-zero, it will tell me what are the paths of length 2 which connect different pairs of nodes. Is that clear? If you have any doubts about this, just ask, because this is a important point. Okay. So what did I say? So I said if aij is 1, it implies that there is a path of length 1 from I to j, because there is an edge which connects directly I and j.
Aij equal to 0.
Sorry. Thank you for pointing that out. If aij equal to 1, okay. On the other hand, if aij equal to 0, okay, it tells me that a connection does not exist from I to j, but I may be interested to know something like this, that although a connection does not exist from I to j directly, can I go from I to j via some intermediate node? So this means that, so the question that we ask is it possible to find a path of length 2? Or for that matter, is it possible to find a path of length 3? Okay, and so on. So if I just focus on the adjacency matrix, this does not give me that information. Okay, but if I use the adjacency matrix in a slightly more devious way, I can actually answer this question, because I look at this and I say that, but wait a minute, what is this? This is just saying that a path exists from I to k and from k to j. Okay, so in other words, aik times akj is equal to 1, right? So if this condition holds true for any k, that means there would be a path of length 2 connecting I and j. All right? For any k can be anything, Now, just think of this in matrix notation. What does this mean? This means that if you multiply a with a, then all the entries which are non-zero, essentially correspond to paths of length 2. Okay. Now I am saying non-zero and I am not saying 1. Why? Because there might be multiple paths of length 2 now. Okay. See, aij was either 0 or 1. You could not have a value 2 or 3 or whatever. Okay. But for when you take a power of 2, there can be more than one paths of length 2. So for example, there could be another L through which you go. Okay. So then if there exists 2 such intermediate nodes for which you have a path from I to j of length 2, you would have a raised to 2 ij equal to 2. Okay. So essentially when you do this operation, this will tell you that if it is non-zero, then a path of length 2 exists from I to j. Okay, and the actual number will tell you how many such paths actually exist. Okay, because if there are 3 intermediate nodes through all of which you can go from I to j, that would give you 3 and so on. Okay, is that clear? Okay, so it tells you not only whether a path of length 2 exists, it also tells you how many such paths of length 2 exists. Okay, so now that you have seen how this works, you would say that, okay, now solving this problem is trivial. I just raise a to the power 3, okay, to find paths of length 3. So whenever a raised to 3, any element is non-zero, it implies that a path of length 3 exists between I and j. Okay. So in general, I can now talk about a path of length r, and I say that a number of paths of length r is simply the ijth element of a raised to r. Okay. So this also actually helps me to count the total number of cycles in the network. Why? So what are cycles? So cycles mean that you start from a node and then following some path you actually come back. Okay. So basically you have a closed loop in the system. Okay. So if you're interested to know the number of cycles, all you have to do is say that what are the diagonal elements of the matrix A raised to R for I. Okay. So this will tell you whether there is a cycle or a closed loop which includes I. Okay. So now you can define these things also for directed network. In directed networks, of course, this is slightly non-trivial because you can, even if paths, even if you have links from one node to other, because of the directionality, they may not actually form a closed loop. So you may not be able to find a path which goes from, let's say, B to E to D to C to B, because if you reverse any one of these arrows, you see that you would break that particular cycle. Okay. But essentially you can now use exactly the same method that I outlined over here and count paths of length r for directed networks and the occurrence of cycles of a particular length. Now, why is this of interest? Because many biological systems turn out to be at least partially acyclic. Okay. Now, how do you find the number of cycles in a network? So I mentioned that the total number of cycles of length r in a network is simply the trace of the matrix A raised to r, and that's because the number of cycles which includes I and of length r is AIIR, and so what you do is you simply sum over I in order to get the total number of cycles. Okay, but what is this quantity? This is nothing but the trace, right? The definition of trace is you sum over all the diagonal elements. Okay. Now, remember your linear algebra 101. Trace of a matrix equals the sum of the eigenvalues of the matrix. Okay. So in other words, if I know the eigenvalues of this matrix, I can just raise them to R, okay, and sum over, and that will give me the number of loops. Okay. So, and if you are interested in acyclic networks, that is a network which has no cycles, whether of length R or any other length, that means for any R, this quantity has to be 0. Now the only way that can be true is if all the eigenvalues are 0. Is that clear? Okay. So suppose I am asking the question that what is the condition that a network has no cycles? Okay. Whether of cycle of length 2 or 3 or 4 or 5. Okay. So what does that translate to? It means regardless of R, summation of eigenvalues raised to R has to be 0. Now the only way that can be true is if all the eigenvalues are 0. Right? And so this tells you that for a network to have no cycles, its adjacency matrix will have to be nilpotent. That is, the eigenvalues are all 0. Okay? So this is a wonderful condition, very simple condition you can use to immediately find whether there exist cycles in your network or not. Okay? And the reason why finding cycles is often important is because, as I mentioned, several biological networks are very close to being acyclic, and one prime example is the case of food webs. Okay? So typically when you talk about food webs, these are directed networks where an arrow exists from a prey species to a predator species. Okay? So you can quite easily view it as a layered network where each layer corresponds to a trophic level, and you start from the base species, which are typically vegetation, to primary consumers, which essentially feed on the vegetation, to secondary consumers, which feed on the primary consumers, and thence on to tertiary consumers, which feed typically on the secondary consumers. Okay? And you find that it's extremely rare to actually find cycles in such networks. Okay? So one can take one's favorite food web and apply this condition to find out whether in fact it's truly acyclic or not. Another case of acyclic network is tree, and a tree is defined basically as a connected undirected network that contains no closed loops. Okay? So usually you define a tree as having a root node, and then from the root node there will be branches, and those branches lead to further branches, and finally they terminate into leaf nodes which have no further branching. Okay? Often trees are used extensively in biology for doing dendrograms. So typically they would show an hierarchical decomposition, typically for example showing the lineage relations between various species. Okay, just a technicality that sometimes just as graphs can be fragmented, just as networks can be fragmented, trees can also be fragmented, in which case, not surprisingly, they are called a forest because the various fragments are those trees. Okay? So one very useful property of a tree is that there would exist only one path between any pair of nodes. Okay? And this is useful to represent a lineage tree because that means that you can define an exact lineage distance between any two species. Okay. Now, going back to the question of paths and path lengths, oftentimes we are interested not just in any arbitrary path, but the shortest path, because we want to know how quickly does disturbance, perturbation, information, signal from one end goes to another end of the network. Okay? So necessarily, you would be considering self-avoiding paths, because obviously if you trace the same edge over and over again, that would not lead you to the shortest path. So in this particular case, for example, the shortest path, or the geodesic, from A to C, you could have something like ABC, which is of length 2, or you could have AFC, which is also of length 2. And so the shortest path length from A to C is 2. And so the general definition is, it's the smallest value of R such that A raised to R, that ijth element, is non-zero, and all the other smaller values of R, those corresponding ijth element, are 0. That means you will not be able to find a path of shorter distance which connects I to J. R is the minimum such path, length of the minimum path. Okay? And of course, if you have two disconnected fragments, you would have an infinite geodesic distance. A related concept is the concept of a diameter. So this basically says what is the maximum geodesic that exists for a given network. Okay? So consider the shortest paths between every pair of nodes. The maximum value of this quantity would tell you what is the longest path that you will ever have to traverse over the entire network, and this tells you the diameter of the network. So I was mentioning Eulerian paths in connection with Euler's solution of the Königsberg problem before. So we now encounter this in a much more technical manner. So an Eulerian path is defined as a path which goes through every edge once and once only. Okay? A Hamilton path can also be defined, which, unlike Eulerian path, which is defined in terms of passing through each edge once, basically says that you visit each node exactly once. Okay? So essentially, this is a self-avoiding path. Now, an Eulerian path need not always be self-avoiding. You might have to go through a same node multiple times, often when you have to exactly visit each edge once and once only. And in fact, it's the Eulerian path which formed the basis for the solution of this Königsberg problem. So let's look at the Königsberg problem once more. So this is a slightly different representation of the bridges of Königsberg. So you have the 7 bridges A, B, C, D, E, and F and G. Okay, and so the question one is asking is that, can you actually find a path which would go through each of these edges once and once only? So you can have a much more abstract representation where you say that these land masses which the bridges connect, namely capital A, capital B, capital C and capital D, correspond to nodes of a network, and the bridges correspond to the edges connecting these nodes. Now, the question of does there exist any walking road that crosses all 7 bridges exactly once now translates to a problem of finding an Eulerian path on this network. Okay. Now, Euler took one look at this network and immediately realized that the answer to this question is no. So the way he argued this is as follows. He said, look, in order for you to traverse each bridge once and once only, each of these nodes must have an even number of links coming out of it, except 2 nodes, the one where you start and the one where you end. Think about it. Is that obvious?
But you were saying that we can break this in a chain. Something like that.
No, not really. In order for you to satisfy this condition that you cross a bridge once and once only, the essential condition is every node must have an even number of edges coming out of it, excepting there are just 2 exceptions, the source and the endpoint. Okay. Now, how is that coming out? That's because if you don't have an even number, if you have an odd number, that means in some intermediate node, that means you can come in, go out. So you use all the 2n edges, but then if you're odd, then that odd edge, once you use it to come in, you cannot go out. Okay. But because that's an intermediate node, you have to go out. Okay. And so this means that for except the node that you start from and the node that you end from, all other nodes must have an even number of edges. But if you look at the corresponding network representation of the Königsberg bridge problem, you find that all 4 have an odd number of edges. This one has 3, this one has 3, this one has 3, and this one has 5. Okay. So regardless of which points, 2 points I start as source and sink, I will never be able to find an Eulerian path because I'll always end up with this problem of an intermediate node having an odd number of connections. Yeah.
Even number of nodes and odd number of connections, and this can
No, the problem essentially just reduces to that you are only allowed 2 nodes to have an odd number of edges, the source and the sink. Okay. Any other nodes, if it has odd number of edges, the problem would be that when you have exhausted all the other edges that is associated with, you are just left with 1 edge. Okay, and using that edge you can come in, but you cannot go out. Even then, you have to go out of that node, right? So the moment you want to go out of that node, you have to use an edge which you already used once before, which violates this condition. Okay. Yeah, it's completely, I mean, that is enough to solve this problem. The moment you find that you have a network where you have more than two nodes which have odd degree, you'd realize that an Eulerian path cannot exist. Okay.
The opposite, like when it will exist.
So as in,
If my both nodes will have like I want to say that if my node will
anyway, we can talk about that afterwards. Okay. Okay. So now, so that's the Eulerian path. Now, what about the Hamiltonian path? So the Hamiltonian path is also associated with an enormous literature, something that Leelavati mentioned in her lecture yesterday. So it's related to this concept of the traveling salesman problem. Okay, so traveling salesman problem is one of those classic, statements of a extremely hard problem to solve, and it's phrased as follows: a salesman needs to travel through n cities and get back home. Okay? And you are given the cities and how much it costs to go from each city to every other city. And so what the salesman is trying to do is it's trying to find the shortest possible route or the least expensive route such that it can visit each city exactly once and then return to the origin city. Okay? And if you want to translate this into network language, you are asking the question that given a complete undirected network that has a non-negative integer cost associated with each link, so that's the cost of traveling from one node to another, or maybe it's related to the distance, you're asking, is there a Hamilton cycle having minimum cost? Okay. Now, for a few cities, like if you're like dealing with something like order of 10 or so, you can still use a computer to find it, but quickly it becomes extremely difficult to solve with increasing n. Okay. In fact, it's known to be an NP-hard problem. Okay. There are no polynomial time algorithms to solve it, and as Leelavati mentioned, in fact, it's mappable to a whole series of problems occurring in different areas, including the shortest superstring problem that she mentioned, which is very important for sequencing. Okay. Okay. So that was a short tour of all the metrics which are associated with a global property of the network, namely how quickly can I traverse from one end of the network to the other end of the network. But I may be interested in more local properties like that of centrality. Okay, so this is something that we have encountered before when we talked about Google. So as we mentioned over there, this local properties of centrality measures how important a node, or for that matter a link, is to the entire network. Okay? So you can define centrality in very different ways, as I mentioned, and the most common definition is degree centrality, or simply degree. So this just asks how many connections a node has. So the more connections a node has, the more important it is, the more central it is in some sense. Okay? But you can also use, as we saw in the case of Google, eigenvector centrality. Okay? So eigenvector centrality is a generalization of degree centrality, because in degree centrality you are only looking at your immediate neighbors. How many immediate neighbors do you have? Okay? But if all your immediate neighbors are extremely unimportant, each of them do not really have too many connections, you may not be very important over the entire system. Okay? So eigenvector centrality takes care of this by saying that your importance is not only associated with how many nodes you're connected to, but how many important nodes you're connected to. Okay? And that's because all neighbors are not equally important. Some are more important than others. You could also define other measures of centrality, like for example closeness centrality, which says what is the mean shortest path length starting from this node to the entire network. So starting from some nodes, it may be possible to travel to other nodes using much shorter average path length than starting from other nodes, and that essentially gives differences in the closeness centrality of different nodes. And finally, you can have betweenness centrality. So this is the concept of gatekeeper nodes that I mentioned very briefly in yesterday's lecture. So you could have a node which essentially is acting as a bridge between two large clusters. Okay? So if you take out this particular node, you would essentially remove any connection between these two clusters of the network. So its importance lies in the fact that to go from any point of this cluster to any point of the other cluster, you necessarily need to travel through this particular node. Okay? And just as you can define, these are all defined in terms of nodes, you can also define them in terms of edges. So you can talk about betweenness centrality of edges, where you say how frequently is a particular edge travel through in order to go from any node to any other node. So let's look at degree in some more detail. Okay? So as briefly mentioned in yesterday's lecture, you can calculate the degree of any node simply by taking a row sum or a column sum of the adjacency matrix for an undirected network. Okay? And the total number of connections in the network, as we saw in the beginning of today's lecture, is simply you sum over all the degrees and you divide by 2. Okay? And the division by 2 is basically to take into account the fact that the two ends of every connection essentially contribute to the degree of two nodes. So the mean degree of a network is related to the total number of connections L and the total number of nodes, as we saw. If all nodes have exactly the same degree, so if average degree is the same, if Ki, the degree of each node is exactly equal to the average degree, then you have what is known as a regular network. And one of the simplest examples of a regular network is a ring, because every node has exactly two connections to its two neighbors, left and right. So that will constitute a regular network. Again, these are something that we have seen before. The maximum possible number of connections in a network with n nodes is simply NC2, and we often express the so-called connection density of a network in terms of the ratio of the actual number of connections L to this maximum possible number of connections. So in a sense, this is like what is the probability of connection between any two nodes in the network. So that's related to the connection density. Now, why is this of interest? Because by knowing how this connection density behaves as the network becomes large, you can define something qualitatively about the network, whether it is dense or sparse. So technically speaking, a network is dense if its connection density tends to a constant as n tends to infinity. Okay? On the other hand, it is a sparse network if, as the network becomes larger and larger, the connection density goes to 0. Now, if you just look at how rho is connected with k, you would immediately realize that the sparse network would be one where the average degree tends to a constant independent of the size, whereas for a dense network, the average degree would actually increase with system size. Now, this is an important question when one is dealing with biological systems, because often we'd like to know that is a biological system following constant connectance or constant degree? Is it dense or is it sparse? And case in point, for food webs, this is an extremely challenging question which people have tried to answer using lots of empirical data, but still no answer, convincing answer seems to have emerged. So there is one hypothesis which says that there is some kind of a link species scaling. So the number of links per species in a food web is constant. Okay? So regardless of how many species there are in an ecosystem, typically a species will feed upon only k other species. Seems to make sense, right? I mean, if I'm used to more or less having 10 different types of food sources, I would stick to that, regardless of how many other species have joined the network subsequently. On the other hand, there is the constant connectance hypothesis, which says that if you have a much richer ecosystem, so if you double the number of species, then essentially species link to many more other species. So their sources of food becomes much more variegated, so that essentially the average number of connections is higher per species for ecosystems which is much larger. Now you would say that why not just look at the empirical data and see which of these hypotheses is true. whether it's a constant degree or constant connection density. The problem is that the data doesn't seem to fit any one of these hypotheses over the entire range of ecosystem sizes. So this is the number of species in ecosystem S, and this is the number of connections L, and so you can see that one of these curves corresponds to L going as the square of S, so this is the constant connectance hypothesis, and the other curve basically has L proportional to S, so this is the linked species scaling, so that you have constant average degree. Now what you note is that if you actually try to do a regression fit, the best fit is like S raised to about 1.5. So it's clear that nature does not seem to follow either fully the constant connectance hypothesis or fully the linked species scaling law. The best guess is that it probably does something like this. For low system sizes, it follows the constant connectance hypothesis, but at larger system sizes, it goes over to the linked species scaling where the degree becomes constant. Why it happens is of course an enormous field of speculation. There are loads of theories which tries to say why is it that as you go to larger and larger system sizes, average degree would tend to become constant, whereas for smaller system sizes, typically average degree would scale with system size. Just as you defined paths both in undirected and directed network, similarly you can define degree for directed network. Now, since you can now have a path from A to B as well as from B to A, it makes sense to now talk about incoming connections and outgoing connections separately. So now you can define an in degree and an out degree, where in degree, as the name makes it clear, is the number of incoming connections and out degree is the number of outgoing connections. Okay? So you can get one of them by just doing a row sum and the other by doing a column sum. So unlike the undirected network where the row sum and the column sum used to give us the same quantity, namely the degree, here because it's directed, now the row sum and the column sum are going to give me different quantities, namely the in degree and the out degree. However, the total number of connections is still the same, so you can just get this by summing over all the in degree or summing over all the out degree, and not surprisingly the mean in degree equals the mean out degree because this quantity L, which is divided by N, so both L and N are basically unchanged, so therefore you will get mean in degree and equals the mean out degree. Now you might well ask that does a node which have high in degree typically tend to have a high out degree? Okay. Now a related question is, if you have a particular distribution of in degree, would the distribution of out degree also be similar? Now that turns out to be not true. So for example, this picture shows that for transcription factor binding network as well as for phosphorylation network, which is important for intracellular signaling, the in degree follows an exponential distribution while the out degree follows a heavy tail distribution. Okay. So think about it. So it means that typically the number of incoming connections tend to have a very narrow range of variability. Okay. So typically the number of incoming connections would vary from 5 to 25. Okay. But the number of outgoing connections, the number of connections you could give out to other nodes, that has a huge variability. So it varies from something between 5 to 500. Okay. So whereas you would be saying that essentially all nodes are roughly similar in terms of the incoming connection, in terms of their outgoing connection, nodes could be very different. So nodes which have outgoing connections of order of 500 would correspond to hubs, whereas nodes which have only about 5 connections would essentially be relatively unimportant nodes of the network. Okay. Why is it that outgoing connections tend to have different distributions, namely a heavy-tailed one from in-degree connections, happen to be related to the way the networks are created and also the way the networks function. Now, related to this question of would a high in-degree node also happen to have a high out degree, is the concept of reciprocity. Okay? So you can ask that if I receives a connection from J, does J also receive a connection from I? This would be a question which is relevant in lots of different biological networks. So for example, in neural networks, you could well be asking the question that, let's say a synaptic connection exists from A to B. Does a reverse connection also occur? So this is measured by the reciprocity function, which is essentially looking at the product of this quantities Aij and Aji and averaging it over the total number of edges. So not surprisingly, this is nothing but the trace of A raised to 2. So this essentially defines a reciprocity measure. You can of course also define it in a different way as essentially the correlation coefficient between Aij and Aji. Now, if you measure this, you find that different biological networks have very different properties when it comes to reciprocity. So for example, neuronal networks, in specifically the chemical synapses of the Sinha elegans, shows reciprocity. Metabolic networks also show reciprocity, although it's weaker than the neural network, but food webs are actually anti-reciprocal. And that's kind of makes sense because in food webs, typically if you have a connection from, since you have connections from prey to predator, reciprocity would mean that the predator would also become the prey of its prey, so which is kind of nonsensical, right? So you can actually say quite a few things about a biological network simply by perusing all these local properties of clustering, reciprocity, and so on. Now, reciprocity typically is defined for directed networks. Now, you might say, is there a generalization of this for undirected networks? Now, for a pair of nodes, this doesn't make sense because a connection either exists or does not exist. But for a triad of nodes, that is, if you consider 3 nodes A, B, C, now we can actually consider a very similar quantity. We can talk about transitivity. Okay, so we can say that if A connects to B and B connects to C, is there a connection from A to C? Okay, so this is in fact related to the very general mathematical concept of transitivity, where essentially a relation is said to be transitive if RAB and RBC implies RAC. Okay? And of course, the simplest of such transitive relations, for example, is equality. So another way of expressing transitivity is to say that a friend of my friend is also my friend. Okay? So if this property holds true in your network could be said to show transitivity. Of course, no network would show complete transitivity except for cliques, where every node connects to every other node. So typically you're looking for evidence of partial transitivity, which is basically saying that if 2 nodes I and G are connected and another set of 2 nodes J and K are connected, then it's very likely that I and K would also be connected, forming a closed triad. So when you're trying to measure how transitive your network is, you calculate a quantity known as a clustering coefficient. So this is basically the fraction of paths of length 2 which are closed. So in other words, if you have you remember that I was talking about paths of length 2. So A and B would have a path of length 2 if there's an intermediate node C through which a path exists between them. So now what we are saying is that consider all paths of length 2 between A and B and ask how many of these paths for every pair of A and B considered is actually close, such that a connection actually exists between A to B. So this would help you figure out how much transitivity actually occurs in the network. So depending upon how you define it, you could have 2 different measures. So one is basically a global measure. So you're simply counting the number of triangles and you are dividing by the number of connected triples. There's a factor of 3 that you have to take care, because each triangle can be counted as ABC, BCA and CBA. So you need to take that into account. But this ratio essentially would tell you how many total connected triples would be there in your network. But you could also define it in terms of local clustering coefficient, where you're saying that consider each node I, consider all its neighbors. Okay? Ask how many of your neighbors are also mutual neighbors. So this fraction, how many of my neighbors are actual mutual neighbors, to the total number of possible connections between my neighbors, defines a local clustering, and then you average over this local clustering to get an average clustering coefficient for the network. Now, the advantage of looking at local clustering is that it often reveals the existence of structural holes. That is, neighborhoods of the network where neighbors are not actually mutually connected. So typically, this often implies the occurrence of an hub which is connecting lots of nodes which do not share any relations between them. So the existence of holes have been connected with breakdown of information passage, and often it's very important to identify such holes in either a social network or a biological network to identify bottlenecks or possible fragile locations in the network which can break down under certain conditions. So clustering is also connected to this concept of triadic closure, which essentially says that if two nodes are connected with a third node, what is the likelihood that they actually have a connection between them? Now, the concept of triadic closure originally arose in the field of social network, where the idea was that suppose you are friends with A and you are friends with B, that makes it very likely for A and B to eventually become friends because you are the common link. Okay? Now you might ask, how is that possible? Well, if I have lots of common friends with some other person with whom I don't yet have a connection, chances are that eventually I will meet this person in some social setting and form a friendship. Okay. So typically in social relations, you find that triadic closure is a very common phenomenon. Friends of my friends eventually become my friends. Okay. And so you ask that, is triadic closure a observed phenomena in other kinds of networks other than the one that you find in social settings? Now, suppose you were considering a completely random network. In such a situation, the clustering coefficient is simply the connection density. Okay, the total number of connections divided by the number of nodes, and that's because if you consider two nodes, then independent of whether they have several acquaintances common, the possibility that they are connected is simply the connection density of the entire network. Okay? So that's why for random network it's fairly easy to figure out what will be the clustering, and this forms a basis, or what you call a reference against which you can compare the actual calculated clustering of a network and ask, is this more clustered than what you would expect by chance? So if it is more clustered than what you would expect by chance, you would say that clearly there is evidence of triadic closure in the network. And the reason why people are often interested in whether a network has evidence of triadic closure is that typically the occurrence of triadic closure results in the formation of modules or communities. Okay? Just one last thing that I'll go through before ending today's lecture is that another related measure is this so-called concept of similarity. And this is often practically very important, because often you have found that when you go to Amazon, for example, it will say that if you like this, you would most probably like this. So you go and click on a book and you say that maybe you will like this other books. Okay. So how does automated algorithm know how to give suggestions as to what you will like? Okay. So the way it knows this is because it has a huge database of other users who have, let's say, clicked various products, and by looking at what kind of things that you have clicked on before and trying to see whether this pattern of clicks is similar to the pattern of clicks by another user, they will try to make an extrapolation. So they would say that, okay, given that you have connected to nodes A, B, C, another user who has connected to AB and linked to E, it's very likely that you would like product E. Okay, and so it gives you a suggestion that maybe you should click E. Okay, so this is related to this concept of graph similarity, where what you do is you look at your network and you ask how similar is the neighborhood of a particular node with the neighborhood of another node. So in this particular case, look at node I and node J. So the neighbors that they have are actually held in common with each other. So in fact, you have an exact overlap between the network of node I and the network of node J. Even if it's not exactly identical, you could have, like for example, the majority of the neighbors of node I being common with the neighbors of node J. So this is measured, or for example, could be measured by a measure like this cosine similarity, where you're just asking how many common neighbors do I have divided by the square root of the product of the total number of connections that one node has and the other node has. Okay. Sometimes you also talk about regular equivalence instead of a structural equivalence, where you say that, okay, I do not need to have exactly the same set of neighbors as the other node to be equivalent to that node, but rather they would look similar. So in this sense, like for example, node I connects to, for example, three nodes of this particular property, and node J also connects to three nodes of that particular property. Although they are not identical, they are equivalent, and so you have a regular equivalence of two nodes. Okay, so I will stop at this point, and in the next lecture we would look at a few other metrics which are related to signed graphs, because signed graphs essentially brings into the mix some qualitatively new features, and then eventually, and what we will do next is to see how now we can use these metrics and calculate simple quantities for networks. Okay, so that would give us some kind of a structural information about networks, and then we can try to see how the structural information can alert us to various functional and dynamical properties that these networks can be associated with.